Hello and welcome to the first lecture of this course. The purpose is to give the fundamental knowledge of the ultrasonic testing, and we will also take a look at how it is used by quality assurance and test personnel to ensure the quality of the finished product. Let's start by taking the definition of the ultrasonic testing first. So ultrasonic testing is the name given to the study and application of sound waves having frequencies higher than those that a human being can hear. Ultrasonic testing begins at 20,000 cycles per second, which is 20 kHz, but the frequencies used in the industry commonly range between 50 kHz and 50 MHz. Now that you have an idea about what is ultrasonic testing, let's go back in time and look at the history of ultrasonic testing. For centuries, objects were tested by hitting them with a mallet and then listening for the tonal quality difference. The natural resonance of an object gave evidence that the struck object was free from imperfections. Every solid object, whether it is a piece of pottery, a cast bale or forged sword, has a natural frequency. The presence of discontinuity, such as a crack or a void, will cause the tone of the object to be different from the one of a normal object. Around 1900, railroad workers tested objects using combination of penetrant and resonance. The idea was to apply kerosene to the object and then cover it with a coat of whiting. Then the object was struck with a mallet. In areas where the whiting became wet due to the kerosene being drawn from cracks, the object was designated for repair. Lord Rayleigh was the first to describe fundamental principles of sound in his treatise The Theory of Sound, published in 1870. Later, in 1880, Pierre and Jacques Curie were the first to demonstrate the piezoelectric effect. And in 1881, a scientist named Gabriel Lippmann extended their discoveries. The sinking of the Titanic had a significant impact in that scientists worldwide began to focus on the use of sound for discovery of icebergs, and in the effort discovered additional characteristics and use of sound waves, including hydrographic mapping, submarine location and tracking. It is interesting that the pulsical method used in the early experimentation with sonic waves was not used in the industry for discontinuity detection until the early part of World War II. In 1929, a Russian scientist by the name of Sergei Sokolov was the first to describe the use of very high frequency sound produced by the use of quartz crystal to inspect casting. At first it depended on the reaction of mercury contained in a cup on the fair side of the test material to display a certain pattern of waves in the fluid to tell the scientist whether the wave was traveling through a sound or flowed section of the test object. In 1935, Sokolov presented a more practical approach to continuous road transmission testing. He used a receiving transducer in place of the gap of mercury which he had used in the earlier experimentation. This new method for testing with sound waves, called Supersonic, and until the war become more readily associated with a supersonic flight in the late 1950s, the name was changed to ultrasound. The original name and its current one were meant to indicate that the vibrations are occurring at frequency too high to be detected by human hearing. In the early 14th, several scientists and engineers began the use of pulsed ultrasound instead of the continuous style developed by the pioneers. Adolf Trost in Germany Donald Sproul in the UK and Floyd Firestone in the USA developed the first pulse deco technique that is used predominantly in the testing industry for today. By placing the receiving crystal of the same side of the material as the transmitter, the pulse echo technique made it possible to display the depth of the material plus that of any reflection returning from an internal discontinuity. Now material can be tested from one side, as opposite to what had been necessary before. Until 1947, discontinuity detection was limited to those that were oriented parallel to the test surface. The ability to find off-angle discontinuities was made possible by Sproul when he devised the method for creation of shear waves that could be introduced to the test material at an angle such as 45, 60 and 70 degrees. This brought immediate opportunities for testing within the welding industry, where there is a high tendency for discontinuity to be oriented along the original bevel face of vertical to the test surface. Another UK scientist by the name of Maurice Silk was the inventor of the time-of-flight diffraction, which has been a critical importance to modern engineers who requires exact knowledge of true thickness dimensions of discontinuity in order to properly calculate according to the emerging science of fractal mechanics. There have been significant and steady advances since the 17th in transducer material, electronics, data handling and storage. All of these have contributed greatly to the enhanced ergonomics evident in today's thickness meters and discontinuity detectors.